Okay, let's make a start. So hello and welcome to the first online edition of the London Machine Learning Meetup. This is our first online session, so please don't expect smooth execution or anything like that. We're going to try and do our best. So first of all, we've decided to change around things a little bit to take advantage of the online format, and it's going to work like this. So first of all, we're going to have Charles Blundell speaking for 30 minutes, but this time we're going to follow with a facilitated discussion, which is going to last for another 20 to 30 minutes. And we've asked previous speaker, Sam Ritter, to be a moderator for the discussion. So for now, all you need to know that the Zoom QA function will be open for you to ask questions as we go along. Sam will help to choose the questions and facilitate a discussion with Charles after Charles is finished. Although Charles, if you want to just monitor the chat or take 10-15 seconds every now and again to monitor the chat, we'll try and highlight any urgent questions that need answering during your talk. But don't worry too much about that. We can always come to them at the end. So everyone in the audience, you can chat to the organizers using the chat function as we go along to let us know if anything's going wrong. And as usual, we're sponsored by Man AHL and Evolution AI. So please talk to Man AHL if you want a job applying machine learning in finance, and talk to us at Evolution AI if you're looking for technology to extract text from scanned documents or PDFs. And you can contact either of us by messaging the meetup organizers. So now I would like to introduce you to Charles Blundell.
Hey, thanks for coming to my talk. So I'm going to be talking about Agent57, which is a deep reinforcement learning agent that we've been working on for a little while now. And I guess the sort of headline result here is that it outperforms all the human benchmark that we've been using on Atari on all 57 games. What I'll talk about today will be two papers, which are linked to here. And there's also a blog post that we wrote to summarize this from a different perspective. So I actually can't, whilst I'm talking, I can't actually see the chat. So if there's any disambiguation questions, maybe one of the organizers can sort of butt in and let me know that there's a disambiguation question. All right. So actually, I would like to first of all give credit to the people who did the majority of the work here, which are Adria, Bilal, Stephen, Pablo, along with Alex and Daniel. Okay, so what are we talking about here? What is like the headline result and what are we interested in? So here is a kind of a typical learning curve. Along the bottom axis is the number of frames that an agent experiences. And on the y-axis here, this is the number of games where the agent is above a human baseline performance. And the human baseline performance, the human baseline was set about 5 years ago. And here I've shown a few agents and how well they're doing after a certain number of frames. So there are 57 games. So the best you can do is you can be greater than human baseline performance on all 57 games. That's this optimal line here. One of the agents we'll talk about today is Agent57. This is the black line here. And as you can see, gradually, pretty quickly, it manages to get above human baseline performance on many games, and then it takes a little while to get the last couple. We actually built Agent57 on top of two other agents. It's based on two other previous pieces of work. One is R2D2, which is this gray line here. And the other agent we built on top of is Never Give Up, which I'll also talk about today, which is this blue line here, which performs worse than the other two agents, but in an interesting way, which we'll come to in a bit. The other thing I wanted to mention is Mu0, which I believe was talked about here a little while ago. This is a successor to AlphaGo, so it's in the AlphaGo, AlphaZero, and the Mu0 lineage. This is, unlike the other agents I will talk about today, this agent is a model-based reinforcement learning agent. The other agents I'll talk about are model-free. But as you can see, these other agents generally outperform it. And this is the previous state of the art, I guess. Okay, so first I want to talk about Atari, why it's a good benchmark. On the left-hand side here, this is actually a video of Montezuma's Revenge, which is one of the hardest, or has, is one of the harder games, I think, in the suite. And this is Agent57 playing it, just to give you an idea of what these games look like. And I guess as a benchmark, there's a few positive things and negative things about it. So as a benchmark, there's a wide variety of games. I'll show you more of them at the end of this talk, just to give you an idea of how varied they are. But there are 57 games, and they're quite different games, although there are obviously certain genre of them. there's a clear metric of progress. So on the left-hand side, in the middle at the top, you can actually see a score. And we use this score for two purposes, really. One is to evaluate how well an agent's doing, but also we use differences in score to provide the agent with a notion of reward, like how well it did is sort of intermediate signal. And I guess another thing about these games is they were created to entertain people. So there's no sense of setting our own homework. We didn't come up with these games to test AI agents. They sort of pre-existed, although there was some selection on which games would be interesting to look at. On the other side, these games are quite simple. So the actual game state is around 1 kilobyte. It's quite small. So these games are not particularly random. And as you can see, they're not particularly graphically rich or anything like that. There's a lot of variety, but the state is not very large. So if you knew what the state was, the benchmark becomes much easier. So if you do things like reset the state and stuff like this, actually the benchmark's not too as difficult as it would be otherwise. And I would also say that looking at these games, Agent57 is doing a pretty good job actually in Montezuma's Revenge. There are various bits of it that require a great deal of patience. So this maybe doesn't fully capture everything we'd like to capture about what it is to explore environments and play games as humans. Anyway, but it's been used for a while and it seems it's a very popular benchmark. So if we think about how well have we done, here is a sort of plot summarizing, I guess, the last 5 years worth of progress. Not every paper is on this, and it's a sort of a subset that we could easily get results for. So I guess the early results would be A here, which is deep Q networks. This was one of the early papers from DeepMind. So it's a deep reinforcement learning agent. It's model free. It gets about a 70% median human normalized score. So what does that mean? Well, human normalized score is a metric that sort of standardizes the score across all 57 games. So a human normalized score of 0 means the agent's performing at random, and a human normalized score of 100 means that it's performing at about the same level as the human baseline. And then, of course, for each game, you get one of these human normalized scores, and we want to summarize that into a single number across all games. So in this plot, we summarize by taking the median. So here, A, DQN, is about 70% median human normalized score, which means on 50% of the games, it's getting a human normalized score of at least 70. I guess what's interesting here is over the last 5 years, you can see the general linear trend. Like you could almost draw a line straight through this and predict where in another 5 years we get to in terms of human normalized score on Atari 57, although it probably plateaus at some point. So that's pretty interesting. There's definitely a lot of progress here. The color on the chart sort of indicates different fashions in how people are tackling this problem. So initially, most of the agents listed on the left in this kind of cyan color are extensions of DQN, so extensions of deep Q networks, adding various things like ways of stabilizing learning or better exploration methods, this kind of thing. And then in dark blue, these are some more recent approaches that instead of having a value function that has a single value saying how good it was to take a particular action in a particular state, you have a distribution over different values. So they're listed here. And you can see like, okay, it looks like there's some trend and these are the latest advances. So I guess in this work, we were sort of motivated at looking at a different way of summarizing performance on these games. And on this plot, the next one I'm going to show you, we're looking at the bottom, the 5th percentile of performance. So instead of looking at how well we're doing on some average of games, we're looking really at the worst games. And in fact, 5th percentile corresponds to about the worst 2 or 3 games out of these 57 games. And when you look at this plot, you see there's quite a different story to how well we're doing. So in fact, this looks largely flat. 0 is performing at random. So on these bottom games, for a while we're performing at random, and there should be some other, there's other things you could put just here to sort of fill in the gap, but it's generally pretty flat. Until recently, and there are these 3 pieces of work here, G, H, and J, which are R2D2, Never Give Up, and Agent57. And this is 100%, so this Agent57 is the first agent to be above average human performance. So I'll talk about all of these 3 agents today. I guess another thing I should point out is if we look at the best agents, this is back to the median score. So the best agent by median score on this plot is a distributional RL agent called FQF. It's labeled as M on this plot. In the next plot, though, it's labeled as I. And as you can see, actually it does extremely well on median, but actually on the tail of the distribution, so the outliers, it performs, really there's been no change to how DQN performs, which is very interesting. The other thing I'd like to point out is a different coloring that I think is also quite impactful on performance. So one thing that we've been doing is distributing our agents across many machines. And this allows us to basically get through many more frames at a higher in fewer wall clock times. So we can run things, sometimes overnight if we're lucky, whereas previously we'd run for months and months and months. So this has been very important. So the dark blue agents are these distributed agents. So all of the agents I'll talk about today are distributed. They run across multiple machines, whereas the early agents were all single machine agents. Okay, so now I'm going to talk about how we got to Agent 57, starting with deep Q networks. And I guess the first thing that happened with deep Q networks, so it was released in 2015, is a bunch of improvements that essentially stabilized learning and then scaled it up. So double DQN, prioritized replay, and dueling heads, to some extent, they're all about stabilizing the gradients that go into it, because RL has quite noisy gradients and help stabilize learning of the value function in deep Q networks. And then people start to look at distributing these things like Apex and stuff like that, where you run this agent on multiple machines. And then I guess early last year, of course, people have been looking at combining deep Q networks, which is a feed-forward neural network, with things, short-term memory models like LSTMs and GRUs. But an interesting piece of work was done called R2D2. The first author was actually Stephen, who also worked on this work. And what they did there is they found a way of combining training LSTMs, or these recurrent neural networks, in RL with replay that was very effective. And that was one of the first sort of early peaks in this tail of the distribution of performance in Atari 57 games. After that, my team had been looking for a while at exploration and episodic memory. And we tried a bunch of things, and they'd made some progress. That some of the previous points were things that we'd done. However, we started to think about, actually we carried this work out on episodic memory as two sort of independent strands. And we started to think maybe we should combine them together. And so in Never Give Up, which is one of the papers we'll talk about today, was late last year, we looked at combining episodic memory with exploration. And this proved to be extremely fruitful. But it was not the final solution, I think, to how you get above human level performance on all 57 Atari games. For that, we needed a few more tweaks. I guess one of the major ones was adding a meta controller. So as you can imagine, as you start combining components together, you get a number of hyperparameters. There's roughly, I think, 4 important hyperparameters in Agent 57. So we added a meta controller, and this meta controller sits in the background and it tweaks these hyperparameters to try and find the best values. There's a lot of previous work on this. I guess some of the things like population-based training or metagradients. There's also some work on very simple algorithms, actually, very effective basic bandit algorithms that work very well for this. There's adaptive bandits, which is a recent paper from Tom Schwall and co. and Diana at DeepMind, and also general bandit algorithms. Actually, we take inspiration from bandit algorithms to come up with a simple bandit that controls some of these hyperparameters, which I'll describe all of this in a bit more detail. Okay, so here's a high-level picture of what are the parts of Agent 57, and I would say we don't necessarily believe that all these parts are necessary to get above human level performance in all of the games, but what we found is they're sufficient. So there maybe you can do further pruning of this or further simplification, but at least with these things, we can show that you can get above the human baseline on Atari 57, which previously wasn't possible. And you'll also find papers that suggest some of the methods we're using here, maybe that's not the right way to do it. Turns out it was. So these are the 3 components. So first, we'll start with the actors. Now, the actors kind of do exactly what you imagine. They take actions in an environment. So they are really the part of the agent that sends actions to environment and then retrieves the reward coming back. I guess one of the things that's different in Agent 57 is when the reward comes back from the environment, we also add an agent's own notion of reward, like it starts to reward itself for doing certain things. And this is what drives the exploration that Agent 57 does. Now, the actors don't actually really do any learning. They update things to do with the calculation of the intrinsic motivation, but largely they just run the networks they've already got. And they collect data. And then they send this data to a replay buffer, which gathers agent experience. So you can think of this replay buffer, I guess, as just a kind of database. And then what happens is this just stores things. This stores tuples of the state you've been to, the action you took, the reward you got, and then sequences of these. Now, the learning really happens in another process, a learner, and it minimizes a bunch of reinforcement learning losses and also losses that help calculate this intrinsic motivation, this reward scheme that the actors use to drive exploration. And the learner collects data from the replay buffer. There's some prioritization in the sampling, and there's various statistics that get sent back and forth. And then as the learner advances, it sends its network weights to the actors, so they change the policy they're executing. This architecture is relatively common. This is sort of a basic, the basic way you do distributed reinforcement learning with a value-based or a sort of a Q learning-based method. So actually we built an R2D2, and then for Agent57, then we did Never Give Up. And then on top of that, we've also built Agent57. Okay, so here's a basic idea, just to give you an idea of how R2D2 works. As I mentioned, there's these three components, but really the replay buffer is kind of this database that sits on the learner. That is usually good to have it close to the learner because the learner kind of makes a lot of calls into this database. So I'll describe these two parts, and I'll do this for each of the agents so you can see how things change as we advance the agent. So the actors, there's usually many of them, we use about 256 of them. They're CPU based. This doesn't mean we put them all on one machine and with 256 CPUs, which is quite hard to find. They can be many different machines, that's okay. And then each actor has its own fixed exploration rate, epsilon. So this controls how much exploration that particular actor does, and it's fixed for the lifetime of the actor. And then what happens is the actor receives a state S from the environment, and it must pick an action, then sends the action to the environment, and it gets a reward for it, and then just kind of repeats. So this is sort of the loop that the actor does. And it also, at the same time, as it collects experience, it sends it to the learner, and it receives parameter updates from the learner. Now, the question is, how does it pick the action? So as I mentioned, this is exploration rate epsilon. So what it does is with some probability epsilon, it picks an action completely at random. So uniformly amongst all possible actions it could take. Otherwise, it picks an action that maximizes its value function. So Q here is our value function, and it says, if I'm in state S and I take action A, how much return, what kind of score would I expect to get? And so it greedily picks the best action it could take. So this is really, it's kind of exploration at random, right? So it's randomly picking at random time, it picks a random action to take. Otherwise, it's very greedy with respect to whatever it's learned so far. So that's what the actor does. And then the learner there's usually one of them. And sometimes we use multiple GPUs, sometimes just one. We use the GPUs because this is really what accelerates learning allows. This is really where the computation is spent, the majority of it, I guess, per machine at least. And what happens is it samples a trace. Now, a trace is an idea introduced in R2D2. So often, I guess before this, people would sample tuples of the state, the action, and the next state, and the reward, like the one sent by the actor from a replay buffer. Here, what happens in R2D2 is you sample a whole sequence because you're training an RNN, and then you unroll the RNN, which forms the Q value, the value function Q. And for the first, say, 20 to 40 steps, you don't apply any losses. So this acts as a kind of burn-in where the hidden state of the RNN equilibrates. It kind of goes to a steady state. And then after those 20 to 40 steps, then you start applying a loss on the values output by this network to regress them towards the target. And the target here is very much like Q-learning. Actually, this max operator it's something slightly different, but you can think of it as a max operator. So it's saying my value at in state S, taking action A, is roughly the reward I get immediately plus a discount factor multiplied by what I think I would get in the future. Actually, R2D2 here uses a different backup operator. It's based on importance sampling. But anyway, it's minor detail, I guess, and you can see the paper details of that. Anyway, so there are these two components to R2D2. But I guess one of the things that sticks out as slightly inelegant, at least to me, is this exploration rate. And it's been a bit of a sore point, I guess, in reinforcement learning for a while, that this very simple scheme seems to work quite effectively, but it seems relatively uninformative. So the time at which you do that you take an exploratory step and what exploratory step you take is completely random. It seems like we should be able to do better. So here's sort of some intuition about how we might do better at exploring. So let's imagine the set of all states. So all of the states that exist in some reinforcement learning problem, and I'm going to draw them inside this circle. And I'm going to class them into two sort of categories. states that you visited that are known and states that are unknown. And so when an agent first starts in an environment, all the states are unknown. So all of this circle should be completely read at the beginning of learning, at the beginning of executing anything. But gradually, as the agent explores the environment, this center bit, this set of known states, gradually increases. And what we'd like to do to get good exploration is we'd like to increase the rate at which this green circle, the set of known states, it gets larger and larger and larger. And so the way we're going to do that is we're going to incentivize the agent to head towards these states on the frontier. So this orange bit I've drawn here, this is where we would like to incentivize our agent to get there. And the way we're going to do that is we're going to change the reward mechanism. This is a technique known as intrinsic motivation or intrinsic rewards. So the idea is that if you look in the bottom right, this is the reward the agent's training with. And usually we have an extrinsic reward provided by the environment and an intrinsic reward that's generated by the agent. And so the idea is you take the reward the environment gives you and you add a bonus to it when the agent's doing something it thinks is good. So the question is, like, what would be good? Like, what should we incentivize the agent to do? And so what we do is we look at state novelty. So consider some state that exists in this frontier of interesting sort of known states where we can get to unknown states. And let's think about how we'd like that novelty to evolve over time. So if you've never visited this state, it's really an unknown state, we'd like the novelty to be high. This is a very unusual state, or something you don't know much about. And then as soon as you visit it, so visits are denoted by this purple line, and the novelty drops very rapidly, so you don't go there again. And then when an episode restarts, we're going to some extent forget that we went there to encourage repeat visits. So each time you visit it, the novelty decreases, and when you reset the episode, it becomes novel again. Now, of course, one desirable property is that, okay, short term, you want that to happen, but also over the long term, as you keep going to these states, you can imagine the frontier is starting to increase, and these states that were previous frontier states become less interesting. So there's a gradual general trend of decreasing the novelty over time, over many episodes. So there's these two parts to it. One part, which is a very quick reduction in novelty when you go to a state that when you visit a state, and then there's a gradual, slower, sort of lifelong reduction in novelty as you keep going back to that state. So this was sort of the motivation for Never Give Up, which was some previous work this is all based on.
Charles,
Charles,
just a question from the audience. This is from Elko Bakker. I think it was from 2 slides back. The question is, sorry if I missed a step, but does that actor have a short-term memory state, like an LSTM kind of state? And is that part of the state S? So this is a question about the actors.
Yeah, it does. Yes, absolutely it does. So this Q here is an RNN, and you can think of the LSTM state as being part of the state. Absolutely. Yeah, it's like a summary of the history. Yes, great question. Thanks very much. Okay, so now let's think about these. So I mentioned these 2 timescales of rewards. It's of intrinsic motivation. There's one that slowly adapts to new states. This is the lifelong novelty, and it persists for the lifetime of the agent. And then there's a rapidly adapting notion of novelty, and this resets every few episodes. And so what we do is we have these 2 modules. So one module is based on previous work called random network distillation, and this works by comparing to some random initialized network to a learnt network to output how novel a particular state is over time. And this is the long range, lifelong, gradual decrease in novelty, and it's driven by gradients that backpropagate into one part of these. And then the episodic novelty module has an embedding network that extracts controllable states and then compares to recently seen controllable states. So it keeps an episodic memory of recently seen controllable states. And we use k nearest neighbor to find the k nearest previous controllable states to calculate a density estimate over how familiar the current controllable state is to previous ones. And this is how we derive the episodic part of the reward. And then we basically multiply these 2 things together. So the idea is that this fast changing episodic novelty is down modulated by the lifelong novelty module. So there's a multiplication between these 2 things. So one question is, how do we extract these controllable states? That seems like a very difficult thing to do. Actually, it turns out there's a very nice technique where you calculate an inverse dynamics model. So the idea is you have a Siamese network, and you feed in 2 adjacent frames, and you ask it to predict the action that went from one frame to the other. And it turns out that the representation you end up just before the classifier saying which action you took to go from one frame to the other generally only captures information about the action, and it generally only captures things about the frames that are controllable. So this is how we extract the controllable state. This is this part here. So I just want to mention that on the learner, all these parts are going to be trained. So the learner will train the embedding network, and it will train the R&D prediction network. Actually, in this KNN bit part, all of the learning happens through the embedding. There's no trainable parameters. Okay, so this is how Never Give Up looks like. I've highlighted in bold the things that have changed from R2D2, just to make things a bit clearer. So whereas before each actor had its own fixed exploration rate, we still keep the epsilon greedy in, but we've added this extra set of parameters for doing exploration. So one thing we've always found very important is discount factor. So the discount factor sort of controls how soon you'd like to get a reward. So a larger discount factor means you focus on rewards further in the future, and a shorter one says you want to get a reward sooner. And obviously, you know, depending on the game, there's going to be different trade-offs, but also depending on how much exploration you're doing, there are going to be different trade-offs as well. We also have an intrinsic reward scale, which is this beta that I mentioned a few slides back here, that controls the trade-off between extrinsic reward and intrinsic reward. So each actor has its own discount factor and intrinsic reward scale. And then what we do is we pick the action as before, but the way we're sort of sneaking this exploration in is we're modifying the reward. So we do this k-nearest neighbor lookup of the embedding of the state to calculate the intrinsic reward. And we also pass it through this R&D network. And then we add it to the reward before we send it to the learner. So that's really how it changes. So there's no direct change in the action selection, except that these parameters that go into Q, first of all, the Q network is now conditioned upon how much exploration the procedure actor is doing, and also this discount factor is using. But then this new reward gets sent across to the learner. And what happens in the learner is that it proceeds as normal, except as I mentioned, it also trains this inverse dynamic model and R&D. So there's a few more parameters that get sent from the learner to the actor, and a slightly different reward that gets sent to the learner. So it's rather straightforward. So now the question is, you know, I mentioned this controllable state. Here is an environment that we sort of came up with to test this notion of controllable state. It's a little diabolical and looks quite confusing. We call it the disco maze. So there is a green agent going around this maze. And if the agent, the green agent, touches the wall, it dies. There are no rewards in the environment. And what we'd like the agent to do is to explore the environment. Now, if you were to do a simple novelty-based exploration mechanism, because the colors of the walls are continually changing at random, even if the agent stood still, it would get novelty reward, right? You'd find it novel because things are just changing. So a purely novel agent, a novelty-driven agent will sit still. This is Never Give Up, exploring this maze. And actually, if you watch it for long enough, you'll see that it actually does depth-first search. So it explores every possible state in the environment that's controllable. It doesn't explore every possible state because, of course, dying, you know, by hitting the walls is a state it could get to. On the right-hand side, this is a comparison between using this controllable state versus others. And as you can see, basically, if you use this action prediction or inverse dynamics model for extracting controllable state, you can get roughly 100% state coverage using this depth-first search policy that it learns without any rewards. If you use anything else, it really doesn't get anywhere. So if you use even epsilon greedy is terrible in this environment because you just spend all your time discovering, you know, novel ways to die. It's not particularly interesting. And other things like other novelty-based methods that I mentioned, they just generally sit around doing nothing. So that gave us some confidence that this would extract interesting controllable states in which to base this exploration. And then we evaluated on Atari 57. Initially, we evaluated on just these very difficult games. So in the table at the top, along the top, these are different games. So Gravatar, Montezuma's Revenge, Pitfall, Private Eye, Solaris, and Venture. And then we have the human scores, the baseline scores. And then the best baseline, this is, at the time of writing this paper, these were the best scores obtained by any agent on these games. And then here we have Never Give Up. And N is the number of different possible gammas, discount factors, and exploration rates. So as you can see on, say, Gravatar, Monsoon Revenge, Solaris, and Venture, it's sort of on par with the very best that was available at the time. Actually, on Pitfall, it was the first agent to get a non-zero score, and actually it's quite a good non-zero score. And on Private Eye, it made some advances. So if we go back to the original thing where it has something interesting about it. What's interesting about it is it's the first thing to make any progress on these very difficult hard exploration games, on all of them. So there was previous work that suggests that Monsoon's Revenge, you could make progress on it, but you wouldn't make progress on other games. Here, actually, you find you do. But then if we look at how well it does overall, so this is comparing Never Give Up to various other agents. And in fact, in terms of the average performance, what you see is actually, in terms of the number of above human level performance games, it's about on par with other things. Actually, it's worse than R2-D2, in which it's based on. In terms of the mean score, it's also worse than R2-D2 and worse than mu0. But the 5th percentile is higher, but it's not that much higher. So it's made progress, but it's not quite there. So the motivation of Agent57 is to improve that. So as I mentioned before, in R2-D2 and in Never Give Up, each actor has its own exploration rate, but also it has its own discount factor and exploration rate. What we do now, intrinsic reward scale. What we do now is we give each actor a multi-armed bandit. So the multi-armed bandit picks, at the start of each episode, picks an arm, and this arm will dictate for that episode which intrinsic reward scale and which discount factor gets used for the whole of the episode for that actor. And that would just change the calculation. So instead of this being some fixed beta for the lifetime of that actor, it will change, or potentially change each episode. And then at the end of each episode, there's a little bit of learning that happens on the actor, which is it updates its the bandit estimates for each of for the chosen arm of the bandit based on the episode return. So this, we're going to have around 32 arms that it can pick. And so the parameters here are just for each arm, an estimate of the return that you'd get for pulling that arm. And then we send which arm was pulled to the learner. The other change we made is we discovered that actually increasing the length of the traces really helped on some games. So that was a small hyperparameter change. But other than that, it's relatively straightforward. There's also another change we made in the parameterization network, which I'll describe next. But largely, these are the sort of high-level changes that were made. So the way we also noticed, as I mentioned, there's a bit of a history in all of these agents in trying to stabilize the learning. So one thing we notice is that the extrinsic reward and the intrinsic reward are on two different scales. So if you think about a very difficult exploration game, you'll get a reward of 0 most of the time. And then sometimes you get a very large reward. Whereas the intrinsic reward will evaluate every single state and say how novel it was. And so you'll continually get rewards for the intrinsic reward. So what we did is we take the value function and we can decompose it into two parts. The first part is just trained on the extrinsic rewards, the rewards from the environment. And the second part is just trained on the intrinsic rewards. And so this parameterization doesn't actually change the value function at all. In fact, this is a bit of maths just to show that because of the linearity of the backup operator we use, you can basically show that by reparameterizing this way is completely equivalent to reparameterizing the previous way. But what it does do is it changes the variance of the gradients going to the different parameters. So these two networks have a completely separate set of parameters, and also for the optimizer, a different set of statistics governing the variance of those parameters, like in Adam, which the optimizer uses. So that helped. The other change we made is the meta controller. And so the idea is that now each episode you have this arm that you pull. It chooses the discount factor and the exploration scale you want to use. I said most of the points I made on the left here, but here's an example. So here's skiing, which is a pretty hard game. So the index roughly says the higher the index, the longer the discount factor and the more exploration you do. So you can see at the beginning of training on skiing, it tends to choose arms which favor more exploration and a greater discount factor. And then at some point it decides, no, just switch it off, right? In Hero, it kind of jumps around all the time. And in Gravatar, it does something kind of crazy at the beginning, but not as high consistently as skiing, and then drops it down quite low. So you can see that varying this discount factor and exploration scale per game has a good impact on performance. And it really does vary throughout the lifetime of evaluating the games. Okay, so how much did each of these changes matter? So this bottom line here, this is never give up. This is sort of our starting point. And the top line, the dark, I guess it's black or blue line, this is Agent 57. And the y-axis here is capped human normalized score. So what we do is we basically calculate the human normalized score on all games, except we don't, if it's greater than 100, we set it to 100. So this number can never exceed 100. And what we see is basically if we add this, this bandit with the longer traces, this is orange line, you can see it's better than never give up. Likewise, if we add this separating of the networks, it's also better, although there's some degradation towards the end. And actually they're complementary to each other. So if we add both of these to the same agent, we get Agent 57, and it's able to achieve a capped human normalized score across all games, which is 100%. Okay, so here's sort of a summary of some of the results on Atari 57. This is Agent 57 on Atari 57. So the cap mean, as I mentioned, gets to 100%. The number of games greater than human level performance is 57. If we go back to looking at our 5th percentiles, the bottom 2 or 3 games, you can see it's now above 100. So, and that's higher than everything else. And in fact, actually the 10th and 20th percentiles are also better. In terms of the mean and median performance, we are outperforming both Never Give Up and R2D2, although R2D2 without retrace, it's sort of similar. But mu0 is doing better. So in terms of the average performance, mu0 is doing much better, which I think is on a few games that really smashing it. Okay, so that's it basically. So on the left-hand side, I'm going to show, this is skiing. So this is I guess the game that takes the longest to learn. It's kind of, you might be familiar with it. It's kind of one of these go down a ski slope and get through the slalom flags. One of the reasons it's really hard is because as you get towards the end of the slope, there's a last set of flags you have to get to. And if you don't finish the level and you don't get any reward. So this game is pretty easy to get good performance, but to get human level performance consistently on it, this is the reason we have to run for quite many frames. On the right, this is Pitfall. This is the game where we have the first agent to get above 0 performance. It's kind of an interesting game. It's actually procedurally generated, and you have to travel through many screens before you get any reward. So it's very sparse. And as you can see, here's a reward, a little gold brick you pick up. It's extremely sparse and quite difficult to make any progress on. Right, so I'll end with 2 final videos before we go to questions. These are just to give you an idea of the variety of games that's available. On the left-hand side, this is Solaris. This game is extremely confusing to play. I think looking at Agent 57 play it, it sort of makes a bit more sense. But actually, for a long time, I've had people come up to me and say, well, how do you play this game? Because they can't work it out themselves. It's quite a cool game once you understand it. On the right-hand side, this is just a Country Master to give you an idea of the variety. And with that, I'm done. Thank you very much.
Thank you, Charles. So now I'm going to explain how the QA is going to work. Audience members can add their questions to the QA. I can see a couple of people have already added their questions. Please raise your hand if you'd like to ask your question yourself. If you don't want to ask your question yourself, we might read your question out for you, but we're probably more likely to choose questions from people who raise their hands. When we call on you, we'll unmute you to answer your question if your hand was raised, and you're going to be asked if you want to follow up after your question was answered, but so don't hog the mic. I'm going to hand over to Sam, who's going to be our moderator. Sam is a research scientist at DeepMind, and many of you may recognize him because he's a previous speaker at the meetup. So over to you, Sam.
Thanks, Martin. And thanks for the great talk, Charles. Some really interesting work. I'm excited to learn more about it over the course of this Q&A. I wanted to kick things off by asking a fairly high-level, broad question about AGI research and where it should go next. So clearly, you know, we've hit a milestone, a very important milestone with this work that you presented. You know, this benchmark suite of 57 games has been a major focus for at least a decade of research, and getting to the point where you can have one single piece of code that you can run targeting any one of these games, leave it going for a day, a couple of days, come back later, and you find that you have an agent that can outperform a human for any one of these games. That's really astounding. And I wonder, where do you think research on general artificial intelligence should go now that this has been reached?
Yeah, thanks, Sam. That's a great question. I guess there are 2 things at least from this line of work. I don't think Atari's done quite. I think that there's a few things I'd like to mention. So the first thing I'd like to mention is that we're training, I guess if we go back to the very first slide, there's sort of a hint here at one thing that I think is important. The number of frames we take to get here. So if you look at this graph, right towards the end, there's one last game that takes a really long time to get there. And this is taking 10 to the 11 frames. This is an astronomical amount of number of frames to get there, and absolutely incredible amount of data to get there. The question is, how can we make it more data efficient? I guess that's one question I think is really important to think about. The other one is, I would say, we're actually currently training one agent per game. So one set of weights per game. Now the question is, can you do it all in one agent? So I think those are two interesting questions to think about. And I think that there are problems with doing that, which is why we haven't done it yet. I think they're quite interesting when you think about general agent.
Interesting. Yeah, that makes a lot of sense. Going from, one algorithm to one trained agent seems like an obvious step towards, something that we would call general intelligence. I guess another thing I'm curious about is what benchmarks do you see as kind of the primary next step? So certainly getting more sample efficiency in Atari, getting one agent to solve it. Do you see other either video games or commercial applications as kind of like the next frontier?
Yeah, I think there's obviously a bunch of interesting things we can look at in other video games, but I think obviously looking at problems in the real world is kind of interesting. Of course, one of the issues there with applying RL to the real world is finding out where are the applications where you can deploy RL such that there's room for the algorithm to explore. So you essentially want an action space where it's essentially safe and that the set of actions is kind of known, that there's an opportunity to sort of tune and make improvements that are valuable. So you can think of this as like, domains where you might think about running a bandit algorithm, but where there's some kind of temporal relationship. So there's a sequential decision-making problem to be made. So yes, I think also in regard to the work we've just done, I guess there's other parts of this that can be sort of stripped out and used elsewhere. So we have a very functional novelty detector. And the question is, I think there's other domains where having a notion of novelty might be useful. And so that's another sort of application we can put this stuff to.
Nice. Yeah, that's really interesting. Martin, did you want to pull out a question from the audience now, or should I I see one actually that's pretty interesting that I can read out if you like.
Unless someone has their hand up, then you should go ahead and read it.
Okay, sounds good. Yeah, so, one audience member, Mike here, is interested. How many CPUs are you training on? I think you said 56 per agent. And also how long, or 256 per agent rather, and also how long does it take? So, it's interesting to see the number of frames that were required and the number of frames from the environment, but how long does it take to get a trained agent with this setup?
Yeah, I guess to get basic performance, it takes about a day. But to really sort of get into this long tail, I don't think we necessarily kept, really good track of how long it took, but it took about, I think it's a couple of weeks, basically. It takes quite a lot of time to get through 10 to the 11 frames,
Nice.
Even if you're using multiple machines. So it takes a while to get there. Yeah. Absolutely true.
Interesting. Okay. Right. So following up on what you were saying just before that last question, I wonder if there are any particular commercial applications that you're excited about given these developments, either for deep RL in general or for this kind of episodic exploration. Yeah, just for any of these methods, do you see downstream industrial impact?
Yeah, I think I sort of touched on this before. I think it's really thinking about applications where you can make decisions or you need to make decisions that will be impactful, but also where you can sort of either justify the cost or you can see the advantage of taking exploratory actions. So in a lot of this stuff, you're not necessarily going to understand why the agent takes a particular action. Like, I think there's a whole bunch of work still to be done on explaining why an agent takes a particular action. However, if you're happy with something almost as a black box optimizer to optimize a sequential decision-making problem, these kinds of algorithms can be very effective. You need a reasonable amount of data. I mean, it sort of depends on the domain, and I would say these Atari games are quite difficult. So maybe in simpler domains, you don't need quite so much data. But I think those are sort of some of the axes to think about. So, there's a degree of safety. So you want something where you can explore safely, and that safety might be that the cost is not beyond what you're willing to accept. You also need something where there's a reasonable amount of data. So it should be something you can execute quite quickly. So I think these are some of the concerns about applying this in the real world. I guess we're gradually working more and more towards more real world things. But even in these quite simple games, there are still challenges, right? So I think there will be, I think there are already some places where these kind of algorithms are being deployed, or derivatives of them, where you kind of extract parts, as I mentioned, like a novelty detector. Or in previous work, we've used ensembles to do exploration, and this was then adopted into various commercial applications at Google.
Just as a follow-up, question, I guess, unless you have access to something that can simulate the environment, then exploration is always going to incur some kind of cost. So, if you wanted to try to think about how to increase data efficiency, so that things just became cheaper to learn in the environment, what do you think some of the broader directions you'd want to be looking at?
So I guess one thing is, I guess there's one application I should have mentioned, which is like A/B testing is a form of exploration, which I think is quite widely used. So I think exploration can be used. In terms of data efficiency, there's a few things there. I think one of the things that still bugs us is that we're doing gradient-based updates, and gradients are kind of slow. We have looked into various things to sort of speed that up, but I think there's definitely work to be done there. Maybe even work on optimizers to improve our optimizers. I think since RMS prop and Adam and that kind of stuff, there hasn't been too much change in which optimizers we use, but it still feels like there could be changes there that would really help us extract more juice from data. So that's maybe one area where we could make some changes.
Thank you. So we have a question from Kai. Kai, I'm going to unmute you. Go ahead.
Hello.
Hey, Kai.
Hey, cool. So this is a question, I guess, Sam, you may also want to weigh in on this. So the work on episodic memory has two sorts of big problems. One is representational drift over time, and the other is actually being able to remember specific events for a very long time period. So do you see any progress in these areas?
Actually, I've not really, I've heard this criticism, I think probably from you before about it, but we don't actually see these two problems. So in terms of reputational drift, what we tend to find in these systems, particularly when you train them in a sort of closed loop fashion, you find that sort of self-regularizing effect. Actually in this work, because we reset the episodic memory buffer so frequently, it doesn't really matter. On your second point on storing things for long periods of time, here we're getting rid of them pretty frequently. And I guess there's this notion of systems like complementary learning systems. So you have two learning systems, one that's kind of fast and doesn't generalize and is quite forgetful, and one that is slower to learn, but generalizes much better. And I think really, if you think about the architecture here, maybe I go back to the diagram. So if we go back to this sort of picture here, we have two systems, right? One which is a gradient-based long-term system. So this remembers things for a long time and it generalizes, though. It learns it in a very distributed representation. Whereas the bottom system, this is a system that is very specific. It remembers, I've been to exactly this state, but it remembers for a short period of time because we reset it every few episodes. So in a sense, like by combining these two systems, you get the best of both worlds. You get a flexible density estimator from the bottom system, and then you get one that generalizes from the top system. Does that answer your question?
Yeah, I guess certainly I'd agree with your assessment. Would you say that out of the complementary learning systems, the sort of gradient-based long-term method could still retain information about very specific events?
No, it generally doesn't, right? So I guess this gets to a degree of an inductive bias on what you want to store there. I also think like I think that also finding examples of this stuff would be quite useful. So if you can think of a data set or a problem where we can sort of demonstrate that, that would be very interesting, because at least in all the stuff we've seen, specific instances generally, okay, maybe here's a good example. Like if you think about what you had for breakfast this morning, you can probably remember it very specifically. So this is an example of you using your episodic memory. Whereas if I ask you, you know, can you make a cup of tea? I would imagine many people can make cups of tea. But if I ask you the specific first time you made your a cup of tea, you probably can't remember, unless something really dreadful or incredible happens the first time you made your first cup of tea. You probably can't remember it. So I think there's this natural bias we have, at least in ourselves, where unless there's something really alarming or interesting happening about something that happened in the past, we tend to remember specific things that happened recently and general things that happened in the past. And that's sort of the pattern we see in the system.
Yeah, and just to follow up on that, just to emphasize a point that Charles actually already made, but just in different terms. I also have not seen those problems that you mentioned, Kai. So like Charles' work on neural episodic control and model-free episodic control showed that, yeah, you can store millions of things over the course of millions of gradient updates, and there doesn't seem to be a problem with representational drift. And then as for the issue of whether or not we can save as many specific events as any given task requires, I think we don't really know yet. I haven't encountered a task in practice that requires the storage of more specific events than we can store in our physical memory. It just feels like right now with slot-based memory systems, we have an embarrassment of riches in terms of how much we can store and how efficiently with like sparse KNN we can query over that memory, over those memory systems. So I really haven't seen tasks that we can feasibly run or that are serving currently as benchmarks for our research that push our hardware systems and the ability of sparse KNN to learn to query to their limits.
I just sort of dig into that whole area a little bit more, Charles. When you talk about episodic memory, is the claim here that the system actually has an episodic memory in the way that cognitive scientists define episodic memory? You know, that the entity, that the system can retrieve specific entities, can say when they happened and where they happened. You know, there's been kind of a debate in cognitive science for decades, really, when people have been trying to figure out whether non-human mammals have episodic memory or not, or whether it's only humans within mammals that have episodic memory. And there have been various quite interesting experiments that people have performed on you know, rats and apes to figure out whether they have episodic memory. And probably in the last 4 years, people have come around to the idea that actually some mammals do have episodic memory, and there's some quite exciting results over the last few years. Is your claim that this system actually has episodic memory, like truly defined, or are you just using the word in a metaphorical kind of way?
That's a great question. So I think there's a few properties of episodic memory that we certainly seem to have here. I guess probably, as you know, as episodic memory is instantiated in the hippocampal formation, there's this idea that it acts as a novelty detector. So certainly one of the reasons we use the term episodic memory is we were motivated by this notion that, one reason you can get this notion familiarity, like I've seen this thing before, but I can't remember specific, some specific details. There's a notion of, I know this, right? I've seen this before. This novelty is something that comes out of episodic memory. I think the various bits of processing that happens, I guess as you go through the we can sort of map on to essentially what this k-nearest neighbor lookup's doing. So there's a few steps in that, at least as far as I understand it. There's some pre-processing of inputs that happens maybe in entorhinal cortex, and this extracts certain features that then gets fed into a very sparse system. So I think that there are certain properties and similarities that I can elaborate maybe at some other time. But there is one, I think, very important thing that is not captured by the system, and I think is quite difficult to capture in many of these systems, and that's I would say this is a model of some parts of episodic memory, but misses out on a very important thing, which is the temporal, like a temporal sequence of things. So one notion of episodic memory is the idea that you can recall snapshots in time, and they have a sequential nature to them. So, for example, I gave the example earlier of thinking about eating breakfast this morning. You sort of have this auto-analytic experience. So you can recall eating breakfast whilst knowing that you're not actually living at that time, but you can see it in sequence, and you can remember certain smells and things like this. I think here, because we're focusing on a controllable state, it can certainly recall things that happen to the environment that it could control. So it will ignore certain noisy things, just like you would in your recall experience. But there is no sort of built-in notion of sequential order or a snapshot or something like that. So on one hand, I think it's some model of episodic memory, but it's certainly not a complete model of episodic memory. It's sort of shorthand that we use to some extent.
Thank you.
All right, so Charles, I just wanted to dive for a moment into the nuts and bolts of the sort of advanced and reinforcement learning methods that you presented today. So I really liked the slide on which you showed this progression from the original DQN back in 2015 all the way to Agent 57. And I wanted to ask you about one of the connections in that diagram. And that's the one, I guess, between R2D2, this recurrent distributed Q-learning method, and your sort of curiosity, intrinsic motivation advancement. So I'm really curious about your intuition here. Would this kind of non-parametric curiosity, intrinsic motivation approach work as well with a different RL platform from this R2D2 Q-learning approach platform, such as Impala, like a policy gradient method, or VMPO, something like a policy iteration method? Or is there something that's really key about Q-learning, or R2D2 in particular, that makes it especially appropriate for Never Give Up?
Yeah, thanks, Sam. Yeah, that's a good question. I think there's a few things to say here. So first of all, typically in policy gradient methods, because they're on policy, you tend not to have a replay buffer. And I think certainly in terms of data efficiency, having a replay buffer where you can recall past experience and retrain on previous actions and sequences of states and rewards that you've taken really helps with data efficiency. So I think in that regard, I think we'd be even less data efficient if we use that stuff. Things like VMPO or MPO and this kind of stuff, there is some hope there, actually. It's kind of interesting to try out. I think there is really value in doing stuff in value space because it's intuitive, right? You're sort of changing the Markov decision process by adding this augmented reward on the side, and therefore you only really expect you can directly map that onto how the value function changes. So this decomposition we used of the value function into these two parts, one that's intrinsic, one's extrinsic, that's a little harder to reason about when you're directly optimizing a policy, because the similar linearities don't really exist, although they might in energy space, but it's a bit harder to do. So I think definitely you can apply these to other places. I'm a little suspicious of doing it in anything that's not off policy. And I'm a little suspicious personally of policy gradient methods because, at least in my experience, there's a great deal of noise in the gradients that makes them very data inefficient, even more so than these methods. But certainly it's interesting to think about things like MPO and stuff like that.
Mm-hmm. That's really interesting. Okay, great. Yeah, so I just wanted to ask another higher level question about exploration and a potential application for it. So when I think about hard exploration problems, I immediately think about StarCraft. So as I understand the matter from the paper that came out from DeepMind recently, it's possible to train a deep RL agent that is competitive with humans in the game of StarCraft if you pre-train that agent with human demonstrations. And what I take away from that is that you can't do that if you try to train from scratch. And I sort of assume that that's because the space over StarCraft game trajectories is just much too massive to explore just with this kind of entropy-based, just random jittering exploration. The action space is too large, the sequences are too long. So I wonder what your intuition is about never give up in that kind of domain. Do you think that it would be a sensible direction of research to try to apply this kind of intrinsic curiosity to a game like StarCraft? And if there are any impediments, like how might those be overcome?
Yeah, that's a good question. It's an interesting one. I think we haven't tried. I think it's probably a worthwhile thing to try. I guess one of the things that's difficult about StarCraft, I think there's probably a few things, but one difficult thing is the action space is extremely large. So, you have all the points on the screen, plus you have a bunch of actions and all kind of, it's kind of a hierarchical control problem. So that makes it seem quite difficult, particularly from an exploration point of view, because the action space sort of multiplies up or actually exponentiates the number of possible trajectories you can have. On the positive side, I think it's probably relatively easy to decode from 2 frames what action was taken in StarCraft. So I think getting the set of controllable states probably won't be that difficult. And I also say that the intrinsic motivation and the calculation we have is not a function of the action directly, it's a function of the what's currently on the screen. So I think it's not impossible to apply it. We haven't done it, but I think it's certainly interesting to see how well it fares. I guess one of the questions about all of this stuff is, and it's sort of something we're circling back to, is what is the right state space to operate in? Because StarCraft seems like, there's this very large state space that you're never really going to fully cover, particularly because there's another opponent on the other side who will respond to any action you take, which further complexifies the exploration process. So then the question is, like, what is a good compressed state space representation to get? So here we have this notion of controllable state, but of course, when you have another agent also interacting environments, it's interesting to think about how would you change your notion of what's controllable in the face of the other agent. Suppose, for example, maybe you can control what the other agent does, but maybe the other agent looks random to you because they're much more complicated than anything that your agent can currently understand. So it seems like you can't control it, so you fail to represent what's going on with the other agent, and it may not work as well. So I think there's a bunch of interesting challenges there to think about applying it to this kind of problem.
We just have a couple minutes left. I can see that there are plenty of questions in the Q&A. We're probably going to go to some people who have their hands up, so put your hand up if you want to ask your question. We have a few questions, people with their hands up. IL Kazin, you haven't actually put your question in the QA, I don't think. I can't find it. So if you can put your question in there, then we can call on you. Sebastian, did you want to go ahead and ask your question? You've had your hand up for a while. I'm going to unmute you right now.
Hello, can you hear me?
Yep.
Yes.
Oh, cool. Thanks very much for your presentation. It was really cool. I had a question in Q&A, but hopefully you won't mind if I change my question to maybe something a bit more interesting. I was wondering, I'm still sort of just getting to know these sort of training deep neural networks and things like that. I was just wondering, getting stuck in local minima is quite a big problem, right? And training very large deep networks is also difficult. I was wondering, how do you sort of tackle that issue with Agent57?
Okay, so actually in RL there's something really useful about it, which is that training is pretty noisy. So you often don't get that stuck. It's a question of, usually the general story is tune your learning rates, use a learning rate schedule. So in supervised learning, it's very common that you use a learning rate schedule of some sort, and that often helps you out. In RL, at least in my experience, getting stuck isn't too bad because, like I said, the variance in the gradient is so noisy. Actually, learning is pretty hard, but generally it's kind of okay. I guess one thing from this work that might be useful, and stuff that I know that other people have used in supervised learning problems elsewhere, I think there's actually some work at Waymo using this, which is things like population-based training. So these meta controllers that sort of sit on the side and tune your hyperparameters as you go along can help with this stuff, because sometimes it's just about getting the right schedule on your learning rate. And that's kind of a difficult, it's almost a bit of a dark art how you do that. There are a bunch of rule of thumbs, like you can look at the norm of your gradients and the weight updates and stuff like this. But sometimes it's just easier to use one of these sort of black box optimizers that essentially looks at your training and tunes it as you go along. And that's certainly what we use here. So this bandit algorithm that I described that tunes the discount factor and also the exploration rate, you could equally apply to learning rates. We didn't, just for simplicity, and also because we have one arm that sort of controls many things, and we didn't want to control too many things with it. But you could certainly do something like that as well. But in general, I'd say just tune your learning rates. Also use Adam as an optimizer. That often helps. You're seeing some of these problems because it does a little bit of calibration with respect to noise in your gradients. But yeah, that's what I'd say. Also, if maybe you don't have enough data, well, there might be a bug. But anyway, these are all possibilities. It is quite difficult in these situations, so I completely empathize with what you're finding.
Charles, maybe
thank you very much.
Thank you for the question, Sebastian. And Charles, if you have any practical advice or any links or references that might be useful to practitioners, that would be really helpful. If you can just pass them to me, I'll send them out. And we're reaching the end. Sam, did you have any last thoughts, or shall we wrap up?
I've got one more question that I could ask if you want. It's up to you.
Yeah, you have the last question. Go for it. Okay,
sure. So, Charles, I was wondering if you could just do a quick compare and contrast of Never Give Up with other, very recent prominent exploration methods for deep RL that people might be interested in, both in terms of, what their mechanisms are and how well they perform. I know Go Explore, for instance, I've been hearing a lot of buzz about, but I don't know if you know of others. I'd be keen about how they compare.
Yeah, I guess there's a few things we can talk about here. Maybe I go back here. So here's sort of a bubble of exploration methods that sort of general class of exploration methods that are out there. Go Explore, I think, is very interesting. One thing I would say about it is that it sort of relies on being able to reset the game state. And as I mentioned, the game state is quite small. So I think that makes it a little bit easier, but it's certainly interesting work. So this works sort of in this bubble of intrinsic motivation, but we also use random network distillation. So this is a notion of introducing novelty by comparing predictions to predictions made by a random initialized network. I think, so one thing that we add over this is that this is quite a slow changing notion of novelty, and we have something that moves quite fast, and that seems like an advantage, although we certainly use R&D. Another notion of novelty is the notion of curiosity. There's a lot of work on this, and exactly what you mean by curiosity really is quite varied, but one way you can think about it is a notion of learning progress. Again, I would say one thing here is that this is quite a slow changing notion of novelty, although it seems a bit more fundamental, right? So it's really like, how much have I learned? That seems like a good thing to quantify. So I think, again, that one of the differences there is we're quite fast in updating. And in fact, I would say in general, that's probably a recurring trend. So density models is another way people do this. So they train a neural network that estimates some density over the state space and then says how novel is this thing that I'm going to. And because they're using gradients to update things, it takes a long time, and they're trying to estimate it. There's really just I think there's this 2 time scale thing is quite important. And I also think having something that kind of updates very rapidly also really helps. Another thing that previous work doesn't really do, so by the way, this rapid updating comes in this sort of episodic memory type architecture. I think also this meta control is also quite important. So in most of this previous work, things like coex and reachability, they have one set of hyperparameters, whereas we kind of treat hyperparameters, or we think of hyperparameters traditionally as parameters. So we kind of optimize them as we go along. And I think making your algorithm specific to each game and each situation, even each episode, really seems to have some advantage. I guess I could say also we outperform many of these things. So that's, I guess, another comparison. But there's certainly very interesting ideas here. So I think previously there's other notions here, like there's notions of weight uncertainty and stuff like that. I've certainly worked on some of these things, and they're all very good ideas. This just happens to be one that, in this situation, on these environments, has worked quite well. I think probably we'll need other notions of novelty and uncertainty to drive this stuff. But yeah, so I guess that's maybe some summary of an answer to your question.
Excellent. Thanks, Charles.
Okay, thank you, Sam, for the last question. Let's draw the discussion to a close now. Hope everyone enjoyed our first online event. Feel free to give us some feedback. by messaging the organisers via meetup.com or by email. Thanks so much, Charles, for a fantastic talk. Thank you very much, Sam. Really fantastic to have you moderating and facilitating the discussion for us. And I hope to see you all soon. Bye.
Great. Thanks, everyone. Bye.
Thanks, Martin. Thanks, everyone. Bye.